Hello and welcome to 4.5 in our calculus books, which is U substitution. Now, as we've discussed before, when we're integrating, we have a power rule for integration, just like we have a power rule for derivatives. We don't, however, have a product rule. So all this time, whenever we have a product, we have to multiply that out ourselves. Well, in this case, x minus 3 quantity squared is not so bad, so I would just need to FOIL that out and then integrate. Okay. Well, we don't have a quotient rule either, so if I have a quotient, I'm going to have to do that myself as well. So 3x squared divided by x is 3x, and then x divided by x is 1. So that hasn't been a huge problem in the past. Well, the past is the past. We're going to get problems like this. Now, come on, we all knew it was coming, like the slide says. Well, just because there isn't a product rule or a quotient rule for integration doesn't mean we don't have a few tricks up our sleeve. Well, what we do have is a version of a chain rule. So when we see a problem like x minus 1 to the 50th power, no one is expecting you to write that out 50 times and FOIL your brains out. We know it's not going to happen. As educators of high school students, we pretty much know you're stopping at the cube, and probably 2 or 3 of you aren't going to do that. So we know 50th is not going to be something we want to do. So when we want to think about this, we want to think about it as a chain rule. Something, some quantity being taken to a power. Well, U substitution is kind of exactly like what you think it would be. We are going to substitute something out. Well, it's the x minus 1 that's the problem. Because if I had x to the 50th power, I could use a power rule. So what I'm going to do is I'm going to sub out the u. We've also talked about how important this differential is, because that's telling us what is changing in power, who's changing. So if I substitute the x's out and I have u's, I can't have a dx in there because then that would mean I would increase powers of x. So if I substitute this out, then I also have to substitute this out. Now we have to do it legally because we need to make sure we have the proper du for the u we have now created. So what we're actually doing is whatever you let u be, you're going to differentiate both sides. Now, I took a little shortcut here. When I take u equals x minus 1, I'm actually differentiating that with respect to x. So I actually would have a 1 du over dx equals 1. Now, we're going to treat this like a fraction, so I'm going to solve for my du, which means I'm going to separate those. So if I multiply both sides by dx, I'm going to have du equals dx, okay? And that's where we are right here. So we are differentiating both sides with respect to x, but then we're multiplying both sides by the dx so that we can separate those. So now I know that I can substitute out the x minus 1 for the u. I can also substitute out that dx. So now this statement is equivalent to this statement. The part of the chain rule that we couldn't handle, we substituted out. So now it's just a power rule. We go ahead and take the integral, add 1 to the exponent, divide by that same amount, plus c. Remember, any indefinite integral is going to have that plus c, that constant. And then we do have to substitute out. If we didn't start with u, we won't end with u. So if you're substituting out x's, you also have to substitute out the dx's. So the chain rule is pretty amazing, but we want to make sure we're using it correctly. So how do we know when we're going to use a u substitution? The first way is if we have a quantity being taken to a power. So 3x squared minus 7x to the 4th power. Now, frankly, we could multiply our way out of that mess, but like I said, you know, to the 4th power, no. To the 3rd power, maybe on a good day. But we're not going to take things to the 4th power, to the 5th power, certainly not the 50th power. So this first one, we could if we wanted to, but we don't want to. This second example, the square root of x plus 2, remember that's just x plus 2 to the 1/2 power, so it is indeed a quantity being taken to a power. Now this one, we're stuck. We can't multiply our way out of this, so the only way to solve this would be through a chain rule. So quantities being taken to a power, and then your all-time favorite, trig functions. Remember how just changing the angle to a 2x instead of a 1x, that created a chain rule? Same rules apply. If I have sine of 2x, I can't integrate that as it is without using a chain rule. Well, what I could do is change this using the double angle formula, but guess what? I'd still need a chain rule to solve it. So if you do not have a 1x or a 1 theta or a 1 whatever, you are going to need to do a u substitution. That angle part is going to be your u. So let's do some examples just to see how bad this is going to get. All right, so when I'm looking at this, I notice I have 3x squared minus 1, that quantity being taken to the 4th power, and then I have this 6x dx. Our rule is if there's a quantity being taken to a power, that screams u substitution. So we're going to focus on that aspect of it. We're going to leave the 6x dx for just a moment. So I'm going to let my u be that quantity being taken to a power. Well, then I'm going to differentiate. And remember, this is actually du over dx, but we're multiplying both sides by dx. So we're just taking that quick little shortcut. When I take the derivative of 3x squared minus 1, that gives me 6x dx. Oh, so now we understand what that 6x dx was doing. It's actually going to play the part of our du. Okay, so this is our u right here. And all of this is our du. So when we do our u substitution, we're going to end up with u to the 4th power du. If you substitute out your x's, you have to substitute out your dx's. If your u is representing something bigger, your du is probably going to need to represent something bigger as well. So once we've got it all substituted out, now it's just a nice pretty little power rule. So when I take the derivative of u to the 4th, it's going to be u to the 5th divided by 5 plus c. Don't forget the plus c. You didn't start with u in your problem, so you better not end with u in your problem. So substitute what u was taking the place of. So it's almost kind of like we want to make sure that we substitute it out, so maybe people don't even know we did it. Maybe they'll think we FOILed it out, took the derivative or took the integral and then factored it back. They'll think we're so smart. Actually, they'll know we used up a u substitution. Okay. So number 5, okay, number 4, I had a quantity being taken to a power. That screams u substitution. Number 5, I have an angle that's not a 1x. Screams u substitution. Now, this is what I'm going to let u be. Look at what we have left. We have 5 dx. I wonder if that's going to play the same role as our 6 dx and that be used for our du. I don't know. Let's see. I'm going to let 5x be our u. So when I take the derivative of u is du over dx, but once again, we're multiplying both sides by the dx. The derivative of 5x is 5 dx. So that 5 dx is going to be totally absorbed with the du. So I end up with cosine of u du. When I take the integral of cosine of u du, that is sine of u plus c. Substitute that u back out. We need to make sure that if we started with x's, we're going to end with x's. So my final answer is sine of x, or sine of 5x plus c. Okay. There's an example for you to try, so look to video 2 and get to going. All All right, so now we've got a couple more problems to do. When I'm looking at this, I see a quantity being taken to a power, so I'm going to do the same type of u substitution I did before. I'm going to let what I'm taking this to the 6th power, that's going to be my u. When I find my du, taking the derivative of the left side, taking the derivative of the right side. Oh, now we kind of see why these problems are a little bit different. Before, they've always taken care of us. Okay, this last slide, we needed a 6x for our du. They provided that for us. Now, they're not providing it for us, but we have to have a 3 times dx. Well, wouldn't it be lovely if we could just put in exactly what we need? Just put a 3. Okay, well, we can't do that because we're multiplying it by 3. We've changed the problem. Now, what we can do is multiply by 1. You multiply by 1, you don't change the value. Well, multiplying by 1 doesn't seem like that much fun. It doesn't seem like it's going to change the problem that much. So what we're going to do is multiply by the equivalent of 1. So what do we need? We need a 3. How do we multiply by 3 without changing the problem? Well, we're going to multiply by 3 times 1/3. Okay, you see where we're going with that? Because that's just a 1, so we haven't changed the value of the problem. Remember that integrals, you can push a constant through the integral. So I want the 3 on the inside, but I don't want the 1/3. So what I'm going to do is pull what I don't need inside the integral, and I'm going to pull it through that integral, and I'm going to put it out in front. Okay. So what I end up with looks like this. 1/3 my integral 3 dx over 3x minus 2 to the 6th power. Oh yeah, they can't hold us down. We are winners and we're gonna win. Now we have exactly what we need for our du, so we're gonna rewrite. Yeah, I'll leave it like it is. So 1/3. Everything up here is my du. All of this is du. Everything inside here, that's my u. So it does need a little bit more work. We know we have to put this into a power rule form. So we're going to bring that u to the 6th up, which is going to cost us our negative. So it's u to the negative 6th du. Now we're going to integrate. That 1/3 is going to stay out in front. We're going to multiply u to the, remember, add 1 to the exponent, divide by that same amount, plus c. And then, of course, we are going to simplify, fix things. This u to the negative 5th, I need to bring it down into the bottom. So I have negative 1/15 u to the 5th plus c. Don't you dare circle an answer with a u in it. So u, what was u? 3x minus 2. Don't forget your plus c. Okay. So now that we don't have a u in there, we can box it up because we're ready to go. All right, so let's look at number 9. Same concept. We have something being taken to a power. Remember that this is a cubed root, so that's a 1/3 power. We have that t to the 4th hanging out, but we're pretty sure that that's going to go with the dt and form our u substitution. U is going to equal that quantity being taken to a power. I don't need that parenthesis, but now that I put the first one, I got to put the second one. My du, if I take the derivative, oh my goodness, that's going to be negative 25t to the 4th. Good grief. I do not have a negative 24 times t to the 4th. Oopsie, dt. But I do have the t to the 4th dt, which is the hardest part. So I need a negative 25, so I'm going to put the negative 25 on the inside. I have to put its reciprocal on the outside. I am only allowed to multiply by 1. So I have to multiply by the reciprocal out in front so that that equals 1. And I haven't changed the value of the problem. I've only changed the look. So I'm rocking that negative 1 over 25 out in front. That's just crazy. Okay. I have u to the 1/3. And remember, all of the rest of this, t to the 4th times negative 25 times dt, all of that is what I need for du. If u is going to represent something big, du is going to represent something big as well. If I have u's, I have to have du's. That's the only way we know that our powers are going to change, is by the du telling us u is changing. So I'm going to add 1 to the exponent, so that's going to give me 4/3, but then I need to multiply or divide by 4/3, which is the same as multiplying by 3/4. Don't forget your plus c. There's a lot of things to remember here. So I've got my 100. U to the 4/3, well, what was u? 3 minus 5. Okay, let me write that somewhat so you can maybe read it. Good grief. T to the 5th, all to the 4/3 power, plus c. Now, just like with derivatives, if you don't want to change it back into a radical, I am perfectly fine with that. You do not have to. You do have to change your powers into, make sure your powers are positive. So what's nice about a u substitution problem is that in the same problem, you get to show me you can differentiate and integrate. So it's a wonderful process. I love u substitutions. You can test so much with so little. 10 is an example for you. Head to video 2. 11 and 12, we are going to do those in class tomorrow, so remind me. They're really exciting problems, so make sure you do not miss being in class. Okay, now we're going to look at definite integrals. Now, definite integrals, you can do these on a calculator, okay? And I have shown you how to use your calculator. But please remember, on the AP test, 2 out of 6 problems you can use your calculator on. 17 problems out of 45 problems can you use your calculator on. So there's a very good chance you will not be able to use your calculator. Also, they like to do the process halfway through. And I'll tell you more about that when we get through the problem. Okay, so when I'm doing a u substitution, the same rules apply. You're looking for a quantity being taken to a power, so u would be a fabulous idea if we chose it to be x squared plus 1. Well, when I take the derivative of that, I'm going to have du is equal to 2x dx. And notice I have everything that I need. Okay, so when I put that in there, I've got u to the 3rd du. Now, when we did this in class, when we did the definite integrals or the indefinite integrals, I always made you substitute back because this was going to be our final answer. So we integrated it with you and then we substituted back. Well, now we need to rethink that process for definite integrals because I have this u, and look how simple this is. U to the 3rd du. Taking the derivative of that, or taking the integral of that, it's going to be super nice. U to the 4th over 4. Why would I want to go back to anything that looks like this? That's going to make my integration, my plugging numbers back in, it's going to make it harder. I don't want to work harder. I want to work smarter. So when we're doing definite integrals, if we're making a u substitution, we don't ever have to go back to x. And the way we're going to make that happen is by redoing these limits right here. Okay? Right now, the 0 and the 2, they belong to x. We want to find out what the limits might be for u. That way we don't ever have to go back to the nasty, complex original. Okay, well, the way we're going to figure that out is when x is equal to 0, okay, I'm going to put that right in there. So when x is equal to 0, u is equal to 0 squared plus 1, which is 1. So the bottom limit was x equals 0, so our bottom limit is going to be u equals 1. That top limit, x was equal to 2. When I plug that in right here to my u substitution, I'm going to have 2 squared plus 1, which is going to be 5. So the top limit used to be 2, now the top limit is 5. Definite integrals, if you substitute in u, substitute those limits out, because now when I do this, this is going to be quite nice. The first fundamental theorem of calculus, remember you want to plug in that top number first, then the bottom number. So you're taking 5 to the 4th divided by 4 minus 1 to the 4th divided by 4. And then you simplify from there. Okay, so you've got your 625 over 4 minus 1/4, so you get 156. Okay. Now, what I was talking about just a couple seconds ago about sometimes they like to stop you in the middle of the process. A lot of times on an AP test, they will give you the original statement, this guy right here, and they'll ask you which of the following is equivalent. And they'll be giving you something that looks like this. And their biggest trick is to see if you'll fall for this guy. Okay? The u's been substituted, but the limit values haven't. So on a multiple choice test, we want to make sure we're not falling for that one. If you change to u's, you have to change your limits as well. So this is a really big thing that they like to do on the AP test, which of the following is equivalent. So we need to know how to do it without our calculator. So let's practice that a bit. Okay, so on Leca 13, we're going to find our u substitution. So u is going to be that angle, which is pi minus x. My du is going to be negative dx. Well, I don't have a negative 1 dx, so I'm going to have to put in that negative. I'm going to have to counteract it with its reciprocal, which is negative 1. That way, I've multiplied by 1 only. So I'm going to have that negative out in there. I have cosine of u du. Let's change our limits. Okay, so if I put 0 in here for my x, I'm going to have pi minus 0, which is pi. When I do pi over 4, pi minus pi over 4, okay, which is pi over 3 pi over 4, sorry. Okay. Alrighty, so now looking at this, I can go ahead and integrate just like we do before. And never mind. You can use your calculator at this point, but I want to make sure that you know how to rewrite it in a nice, pretty u substitution form, changing the x's out, changing out those limits, because the 0 and the pi over 4 belong to x, not to y. So if I wanted to integrate this, I would have the integral of cosine, which is sine of u, 3 pi over 4 and pi. So plug in the 3 pi over 4 first and then the pi. Okay, you should get the answer of negative square root of 2 over 2. Okay, so let's look at u, or number 14 here. Okay, u is going to equal that 4x minus 2. My du is going to be 4 dx. I don't have the 4 that I need, so I'm going to multiply by 4, but then multiply by 1/4. I have to get that proper du. So that simplifies to u to the 3rd du. I need to change my limits. So if I put 1 in here, 4 times 1 minus 2 is 2. If I put 2 in there, that top limit up here, 4 times 2 minus 2 is 6. I would integrate that. So I have that 1/4 out in front. When I integrate u to the third, I get u to the fourth over 4. And then I'm going to put my 6 in and then my 2 in. You might want to go ahead and simplify first. So that would be u to the fourth over 16. And then plug your 6 in, plug your 2 in. You should get 80. Okay, you've got 2 examples for you. See video 2. And I will see you tomorrow in class. Happy U substituting.